What's up everyone, welcome back to the second video of the transformer series. In this video, I'll be explaining what constitutes a transformer, how each of its block operates individually to ultimately produce the output. Again, I won't be getting into the mathematical detail of how each of the block operates because each of the block will have its own video where I'll be explaining it into the mathematical detail. Over here, I'll be giving you a brief description of how each of the blocks operate to ultimately produce the output. Okay, so let's get started. The transformer consists of an encoder and a decoder. Okay, essentially. So what an encoder does is it takes in the source sentence, that is the sentence in the first language, understands it, that is, it understands the correlation between each of the words and how each of the which word comes after which, and basically it tries to understand the language. Okay, and produces embeddings. Okay, so what are embeddings? The embeddings are basically the encoder's mathematical understanding of each of the words in its input, that is the input sentence, so which is for the use by the decoder. So what a decoder does it takes in the secondary language, again just like an encoder understands it. Third, correlates its understanding with the encoder embeddings. That is, it takes in the encoder embeddings as well and tries to correlate its understanding of the secondary language and the encoder's understanding of the primary language. That is, it basically tries to understand how the language is translated from one to the other. Okay, so what is an encoder? So let's start from the bottom because that'll be easier to understand. So in the encoder, the encoder takes the input sentence, that is, let's say it's I am going to school. Okay, let it be the sentence. Then it creates mathematical embeddings with a simple embedding layer. I don't need to explain what an embedding layer is. Then it goes through a positional encoding block. So what is a positional encoding block? So remember when we used to use RNNs or bi-RNNs or LSTMs, what happened was we used to feed each and every word one after the other. First, we used to feed I, then am, then going, then to, then school. But over here in the transformers, we feed the whole sentence altogether. So the transformer inherently does not have the idea of which word comes after which. Okay, so we have to explicitly give positional information that I comes before am comes before going, I and am comes both of them come before going, right? So the positional encoding gives the positional information. Basically, it's a sine or cosine function, which basically gives an output of which word of the positional information. So I won't be getting into the mathematical detail of it. So basically gives the positional information. So okay, so to make things simpler over here, I'll just write it down. Let's say I is 0, am is 1, going is 2, 2 is 3, school is 4. This does not happen, to be honest. This does not happen. It is a little more complex mathematical operation, which I'll be explaining in the positional encoding video. This positional encoding output is split into three parts, that is the Q, K, and V. Okay, now the people who know what attention is, they will understand what Q, K, and V are. But to the people who don't know, I will be explaining it in the next video, what in the attention that will solely be on attention. So there you'll be understanding what Q, K, and V are basically. To give you a brief idea, Q is basically the query, K is the keys, and V is the values. Okay, so what are the queries? Basically, while understanding the language, the model asks questions. Okay, suppose it gets a sentence, I am going to school. So the model needs to know who is going to school. So the model asks itself, who is going to school? The attention layer, with its understanding of the language, returns a key. That key corresponds to I. I is the answer. That is, if the model asked who is going to school, I am going to school. I is the answer. Get it? So basically, Q is the question, who is going to school? K is probably the position. Let's say it's the position, that is I, that I's position is 0 over here as we see it. Okay, and V is the answer, that is I am going to school. Okay, so okay, if now your question is, if we split the same thing into three different information, how is it different information? Okay, basically Q, K, and V, all of these have a trainable variable. It's basically a neuron, all right, which takes the three same informations and produces queries, keys, and values as different sets of vectors. Okay, or matrices. Okay, so this is how it is separated, and the model knows to separate these three informations from the same information, that is the positional encoding output, this part. Okay, so this Q, K, and V goes into the multi-head attention layer. So this is what multi-head attention is. I will later on explain what attention is, and thereafter we will see what multi-head attention is. Once you have the understanding of attention, multi-head attention is pretty easy. Okay, so this multi-head attention layer is followed by an addition plus normalization layer, quite like the resonant you see, which takes this output to produce a residual connection over here. This is followed by a feed forward network, which is essentially a simple artificial neural network, which generally is followed by in a CNN. In a CNN, what happens is there are convolution layers, and is followed by 2 or probably 3 dense layers, right? So this is what a feed forward network is. It's basically 2 or 3 artificial neural networks just ahead of the attention layer to propagate its understanding. That's it. Which is again followed by an add plus norm layer with a residual connection, and this produces the output embedding. Okay, not output, just the encoder embedding. Okay, so this embedding over here is then used by the decoder to do whatever I have listed over here. Okay, so this essentially is one encoder block. Now what is an encoder? An encoder is simply a stack of these encoder blocks. In the paper, they have said they have used 6 encoder layers to encoder blocks to make one encoder. Okay, I forgot to mention the paper in which this transformer was introduced. It is known as Attention is All You Need. It's a fairly readable paper. If you understand what attention layers are, you will probably get what transformers are. But if you don't have the knowledge of attention, I would recommend that you not go through this paper because you will have a hard time understanding it. But nevertheless, I will explain what attention layer is in the next video, totally from the ground up. Okay, so this is one encoder block. Now, what is a decoder? How does a decoder correlate between two different languages? Okay, so what a decoder does is, again, let me start from the bottom. It takes the ground truth translated sentence. Okay, let's say our translator works from English to French. Okay, I don't know what's the French of I'm going to school, so I'm going to be keeping it as translated sentence. I don't want to complicate things. Okay, so this is translated sentence. Okay, so it takes the ground truth sentence, again goes through a simple embedding layer, and again to the positional encoding. Now you have an idea of what positional encoding is. It provides I'm going to reiterate it, it provides a positional information of the ground truth sentence. Then it is again tripled basically into Q, K, and V to go into the masked multi-head attention layer. So what is a masked multi-head attention layer? It is the same as a multi-head attention layer. It does the same thing, but it is masked. So what do you mean by masked? Suppose you want to predict the second word of a sentence, all right? When you're predicting the first word, you have no previous information of what the translated sentence looks like because it's the first word. And to predict the second word, you need the first word, right? To predict the second word, you don't need a third, fourth, or fifth word. You don't need the future words to predict a present word, right? You only need the past words. So what masking does is it allows the model to see only what it has to see to predict the nth word. Okay, so basically when you are predicting the nth word, you are only seeing the first, second, up to the n-1th word, and you are not seeing the n+1 to kth word. That's the future words. You are not seeing this. Okay, so that's what masking does. It masks the future output. So technically you might have a question over here, that is, masking technically means you are probably feeding the first word, then the first and second word, then the first, second, and third word. So basically it's again the complexity becomes O of n, but I would say no, it does not. I'm explicitly saying this, we do not explicitly separate the inputs. We use a masking function, which is a simple matrix addition. You will understand this when I explain it in my attention video. I'll be explaining how masking works over here. All right. So it is basically a addition. It is basically a matrix addition, which does not increase the complexity. It is still O of 1. Okay, it is not essentially O of 1, which I said in the last video, but for mathematical ease, it is O of 1. Okay. Oh, okay. So let me give you a brief example of what attention is. All right. So what attention does over here for this self-attention over here, what it does to understand the source language, let's say over here, I'll be explaining it over here. So suppose you have a sentence, I am going to school. So what attention does over here, it creates a matrix of I am going to school, then I am going to school. Okay, and then it correlates how each word is related to the other. Like I is probably very highly related to school, so it assigns a high value over here, high positive value probably. And it is also related to going very much, but I is probably not very much related to I. But what attention does over here is again provides a high value over here, but okay, all right, I will explain that later. But I is not very much related to am, which can assign a, it may assign a low value to these two. So basically it creates a matrix for all of these. Basically this is a matrix of understanding of how each word is correlated to the other. All right, that is what attention does. That's how the training loop, with the training loop, with the propagation of gradients, the attention layer is better able to understand how each word is correlated to the other. Okay, so that is what an attention does, and over here it does the same thing. All right, so let's get back to the decoder. So this is the mask multi-head attention. This attention layer is for understanding the secondary language. This is followed by another add plus norm layer, which comes from here and is again a residual connection. This is followed by an important part, that is the multi-head attention. Well, it seems relatively easy now that you have a little bit of understanding of what multi-head attention is, but it's a little more complicated because the output from the previous layers of the decoder is just the queries. Okay, we do not separate into Q, Ks and Vs. The Ks and the Vs come from the encoder embeddings. Basically, again, instead of separating this one output into Q, Ks and Vs, we are providing this only as Qs, and the Ks and Vs come from the encoder. So basically we are not separating the encoded embeddings into two different parts. We are just duplicating the same thing into Ks and Vs. And as I said previously, that all these Ks and Vs have its own neuron, it is able to completely understand and separate the Ks and Vs from a single source of information. Basically, Q is W into X if the X is encoder embeddings, WQ into X, K is WK into X, and V is WV into X. Okay, and W is the trainable parameter. Okay, but in this case, in the multi-head attention or in the decoder, the Q's, the X is basically the secondary sentence, and let me say this is Y and this is Y. Change the variable because the K's and V's come from the encoder embedding. Okay, so I'm not getting into the mathematical detail again. You might have a lot of questions. I understand you have a lot of questions. It will all be solved in the attention video. Okay, this multi-head attention layer is followed by another add plus norm layer with residual connection, then again a feed forward network, another add plus norm layer with a residual connection, followed by a linear and a softmax activation function to produce the word, just one word to produce. Basically, it takes a set of words from the sentence, from the translated sentence. It takes only the previous words and predicts the next word over here. Now you have another question, that if the decoder is predicting just one word, then how is it again having a complexity of O of 1 and not O of n? Okay, while training, it has a complexity of O of 1 because, I'm going to reiterate this, we are not masking it one by one. We are not. It is just a simple matrix addition, and the whole process still remains still remains in the complexities of O of 1. Okay, I understand that you're having a lot of doubts over here, but I assure you all of these doubts are going to go away when I explain attention, and in the future videos I explain how a transformer is trained overall. During testing, we predict one word at a time during testing, but while training, the whole thing has a complexity of O of 1. Again, it's not exactly O of 1. Okay, now you have another question. We are already providing the translated sentence. What is it predicting then? Okay, so we are providing a translated sentence for the loss functions and the prediction of the future words. Okay, and while testing, we do not provide a translated sentence. We just provide a start token. From there, it starts predicting the later on words. It predicts one word, which goes on to the input of the second word, and then it predicts the third word, like that. All right. You are having a lot of doubts. I understand that. Again, I will be explaining it to you when I explain how a transformer is trained and tested. Okay, this is not a part of this video. So I hope you have a basic understanding of how encoder and a decoder work together to understand the two different languages, correlate between the two languages, and produce the output. All right. So that's it for today. Thanks for watching.